Good morning. Welcome to my new calculus channel. My name is John Gabriel. And in this episode, or this YouTube video on academic ignorance and stupidity, I'll be talking about a topic that most of you have never really thought much about and have learned about in mainstream academia as an infinite decimal expansion, or an expression. But does an infinite decimal expansion exist? And that's what we're going to explore in this topic. So, you're taught at school that repeating decimals are possible. And yes, they are, but they're just a consequence of trying to measure rational numbers in a radix system where there is no measure for the number. Of course, one of the theorems that most academics are totally ignorant about, and I'm not just talking about math teachers, I'm talking about professors of mathematics, is this theorem here, that given a rational number p over q, where p and q are integers, in a radix system B, then p over q is only expressible in the radix system B if the prime factors of q, if all the prime factors of q are also prime factors of B. So what does it mean when we try to express a ratio in a given system, in any given radix system? Well, we measure the ratio. So for example, if we have a quarter, it's actually exactly equivalent to 2/10 plus 5/100. That's the complete measure, and when we talk about measure, it's by default complete. Measure is not partial or approximate, it is always complete, right? So we can actually state a quarter in base 10 or radix 10 as 25/100. Now, if we try to measure a third, we'll have a major problem because a third cannot be measured in base 10. And it does not have a unique representation in base 10 because even if the threes do go on forever, there is no such thing as forever. So no matter how many threes you can produce, I can always show you innumerably many other ratios with those same significant digits in the first n places as 0.3333. So there isn't a unique decimal representation, but I'll come back to this in a little while. So now, in base 45, for example, a third is 15/45, okay, because 45ths is the first factor column in a radix system that is used to measure ratios, okay. And really what you're doing when you divide is you're measuring. Division, all the arithmetic operators are a form of measure, okay, and division is a measure in which the dividend is measured by the divisor. Okay, so you're actually measuring something. In base 7, the ratio 1/4 has no measure. So for example, in base 7, you'll have a repeatable pattern, which is 0.15151515. Okay. Now, mainstream academics really fancy they are smart when they do things like this. Okay, so you can say 1/9 plus 1/3 is equal to 4/9 and do this. But the orangutans don't realize that that doesn't always work. So if you look at this example that I've listed here, 5/7 has a periodicity of 6. In other words, the repetitions are after every 6 digits, they repeat. And 19 has a periodicity of 18. So let's see how this might be done. So fortunately here, the period of 5/7 divides the period of 11/19, okay, by 6, but that's not usually the case. So in most cases, this won't even work. You can't just sort of say, okay, let's have a rule which says we'll just start where the periods align. No, that won't work. It doesn't even work in this case. For example, if we start just before the period repeats, the answer is wrong. So we'll have this answer here if we start before the period repeats. And again, that doesn't help us, all right? So I can't imagine any idiot sitting and doing this and thinking they're actually doing arithmetical mathematics, because this is the kind of stuff only a fool would do. If two convergent series are added, they must be added term by term, as you see in here. So you cannot rearrange terms in a series, because you'll end up getting really stupid results. For example, if you do this here, where you have 1 minus 1 plus 1 minus 1, and you do some rearrangement, you could end up with one of the possible answers being a half. And this is also known as Grande series, which is really an exquisite bowel movement. I have a video on this, which you might like to watch, in which I detail why Grande and mainstream morons think that this could be true, and why they actually use similar reasoning in string theory, which is based on the rot of rearranging terms in a series. So the properties of arithmetic only apply to finite sums. For example, you can't distribute multiplication over an infinite sum or difference. It doesn't work that way. The operations are finite, and if you try to do that, you'll get weird results like I'm showing you here. So one of the tricks used by the mainstream morons is to multiply by a value by a 10, and then do this little trick here, and then conclude erroneously that 0.333 is equal to a third. But this is misguided thinking. And it's really much deeper than what I'm explaining here. A repeating decimal is a consequence of trying to measure a ratio in a radix system in which there is no measure, right? So this is confirmed by the first theorem in the slide. The next absurdity is the belief that pi and square root 2 are numbers. No, pi and square root 2 are symbols for incommensurable magnitudes. Okay, this is a symbol for an incommensurable magnitude. It's decidedly not a number. They can't be measured. And a number is the measure of a magnitude. A magnitude is not a number. So it's pretty subtle. And if you read my article on how we got numbers on LinkedIn, you'll understand the perfect derivation of number. Of course, set theory has it all wrong, but I'm not going to go into that right now. So if you look at this example here, try using the trick to find a ratio for pi, for example. Of course, you won't find a ratio, because we can prove that pi cannot be expressed in terms of ratio. So then the next thing academics try to do is they want to say, oh, well, it has a unique infinite representation. No, it doesn't. And you'll see why there is no such thing. Because if you give me any representation to billions or trillions of digits, or if you can sit down and just determine the digits of pi forever, if you could live forever, I can always give you innumerably many other rational numbers with the same digits in the same first n places. So there is no uniqueness. And since you cannot ever complete infinity, because there's no such thing as completed infinity, that is only the theory of cranks like George Cantor, who is the father of all mathematical cranks. Infinity has no place in rational thought. It's not even required in calculus. Imagine trying to find a ratio for pi using that laughable trick. So you see this example here. What it says is that there's no value of k that will enable you to find such a ratio. But that's expected, because we can prove that pi is not expressible as a ratio. Therefore, it's not a number. And the difference between pi and 1/3, for example, is that pi is not repeating, but neither pi nor 1/3 are expressible in base 10. So they have something in common there. Okay, you cannot express 1/3 or pi in base 10. What that means is you can measure neither of them in base 10. Did you get that, you moron? I hope so. Okay, so radix systems are used to represent rational numbers, and the idea is to have a unique representation. And as I said, in base 10, neither pi nor a third have any measure. So in any radix system, which is a multiple of 3, 1/3 can be measured, as you see in this example here. In base 3, 1/3 is equal to 0.1. In base 6, it's equal to 0.2, and so on. So academic idiots like to talk about real numbers having an infinite decimal expansion. But there is no such thing. Okay, as I've told you earlier, it doesn't matter how many digits of pi you compute. There are many other numbers, rational numbers, with those same digits in those same n places. Thus, the claim that the expansions are unique is entirely false, because there is no such thing as completed infinity. I hope you've enjoyed this presentation, and that you will join me again at some future time. I encourage you to think independently, not to accept anything your orangutan teachers or professors have to tell you, but to delve into these things and to understand the foundations. So until next time, I hope you will join me again. My name is John Gabriel, and this is the New Calculus channel. Goodbye.